Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 8 of the Summer Invariants Maths competition. This is the last week of the competition, but as always I'll leave a link in the description below with details of the competition. Anyway, this is the problem I'm going to be tackling today. We have p and n, both natural numbers, with p bigger than or equal to n plus 1, and we want to prove that this equality holds. Okay, that is a sum from L equals 0 to n of minus 1 to the power of L times p choose n minus L times p minus n plus L minus 1 choose L equals 1. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to get stuck into a solution. Okay, so there are a few different ways you can solve this problem, but the way I'm going to be showing you is making use of the fact that this sort of notation comes up a lot in combinatorics, and that's the problem. The solution I'm going to provide for you, a combinatorics-esque one. Okay, firstly, I'm going to simplify this left-hand side. We want to prove that this is true, but that's if and only if. Well, if we've got this minus 1 term here, which is a little bit ugly, we want to get rid of it. And of course we can do that by just splitting this thing here into the case where L is even and L is odd. When L is even, minus 1 to the L is just 1. And when L is odd, minus 1 to the L is just minus 1. So we're going to bring all the odd terms onto the right-hand side. So they go from being minus on this side to positive on that side. So this is true if and only if we look at the case, the sum L equals 0 to n, but L even. So we're keeping the evens on the left-hand side of this thing here. And of course the minus 1 term vanishes. So we want to show this holds if and only if this thing here equals 1 plus, and then in the case L is odd of this thing here. P choose n minus L times P minus n plus L minus 1. I'll squeeze that in there. Okay, so this thing holds, the thing we're trying to prove if and only if this bottom line holds. So what I'm going to do is prove this bottom line, and that will solve the problem. Okay, so what I've drawn on the whiteboard here is sort of like a p by 1 chessboard. This thing here, so just a row of p squares, initially which are all blank. But you can see here I've drawn on some of them like a green scribble and some of them a red scribble. So I'm going to colour some of the squares, and we're going to call it a colouring if it meets these conditions here. So firstly we're going to choose some L between 0 and n. Okay, and we're going to have L green squares on this chessboard here. So I've got a green square there, and a green square there, a green square there. Obviously there could be some in the middle here. And then we're going to have n minus L red squares. Okay, so I've got red square there, and again there could be some in the middle there. This is just an example of a colouring. Okay, and now remember, P is bigger than or equal to n plus 1. And the number of coloured squares we've got is simply the number of green plus the number of red, which is n minus L plus L, which is n. And of course there are P squares here, and there are n coloured squares, but because P is bigger than or equal to n plus 1, in particular P minus n is bigger than or equal to 1, that means that there's going to be at least one blank square. Okay, so here you can see I've got 2 blank squares, and maybe there might be some in the middle there, who knows. But yeah, there'll be some blank squares. So we've got L green squares, n minus L red squares, but we also have the condition that there must exist a blank square left of the leftmost green square. Okay, now what we want to do is work out the number of ways we can colour this board here. So I'm going to call that the number of L colourings. So suppose you give me an L. I want to know what is the number of L colourings of this thing here. Well, firstly, let's choose the reds. The reds can go anywhere, that's fine. And we've got n minus L to choose, and there are p spots that n minus L red squares can go. So that's precisely p choose n minus L, i.e. the number of ways there are to choose the red squares. But then, of course, we've still got the green squares to choose. Well, how many squares are left? Well, there's going to be p, because they're associated with p squares, minus the n minus L, which are already occupied by red squares. So this thing here is p minus n plus L. I'll get rid of the brackets. Okay, so we've got p minus n plus L squares to choose the green square from. However, remember the green square cannot go in the leftmost occupied square, leftmost unoccupied square. Okay, so we put our n minus L red squares on. Then what we're going to do is look at the leftmost blank square. So in this case here, suppose we haven't drawn the greens on yet. That would be this square here. The green square can't go there. And the reason for that is because if the green square did go there, then it would contradict this property here, that there'd exist a blank square left of the leftmost green. Okay, so that means that the green must go in any of the p minus n plus L minus 1 squares that are here, I guess. So right of the leftmost blank square. Okay, so that means that that square there is always going to be there, so we can always have this property here. But if we put a green square there, then this property vanishes. Okay, but we need this property to exist for it to be a valid colouring. Okay, so that means we've got p minus n plus l minus 1 squares to choose, to put the green squares in, and we've got l green squares to choose, to put in, sorry. So that means we've got p minus n plus l minus 1 choose l. That's where that comes from here, and this probably looks pretty familiar. This is the thing that we're going to be summing up, as you'll see at the end. But this is the number of L colourings. Okay, so the number of L colourings give me an L, and this is the number of L colourings, i.e. the number of ways to colour this P by 1 chessboard that meets these three conditions here. Now what we want to do is consider the case where L is odd and L is even, and show that there's almost a one-to-one correspondence between the two. So when we sum up the number of L colourings when L is odd, we get the same as when the sum is when we do the sum of the L colourings when L is even. However, there is one case where this doesn't work, and that's where that plus 1 term comes from on the right hand side. So let's go into that in a bit more detail. Okay, so now I'm going to describe a process to show that there's almost the same number of even L colourings as there are odd L colourings. And the way I'm going to do that is, suppose we have a colouring. So in this case, we have this one here. And let's just look at the case. Let's suppose that there are L green squares and L is even. Okay? So what we're going to do is we're going to go along this chessboard to the rightmost coloured square. So in that case, that is this square here, which is green. But of course, that could be red. And we still go to that square. So we're going to the rightmost coloured square. So in that case, it's this one here. And what we're going to do is switch the colour. So it goes from green to red in this case here. So we're going to rub this off and replace it with a red square. Now notice that this is also a valid colouring. It meets these conditions here, except now we've got, well, L minus 1 green squares. So this is going to correspond to an L minus 1 colouring sort of thing. So L minus 1 green squares, but in particular L minus 1 is odd. Okay, we don't really care about the number of red squares, we just care about the number of green squares. But notice that there are now one fewer green squares, because there was green square here before, and we've now switched it for a red. So we've now got L minus 1, but because L was even, L minus 1 is thus odd. Now also, if this thing here was red originally, then what we would have done is switch that red to a green. So we go from L squares to L plus 1 green squares. But notice that either way, the parity is going to switch. So whenever we apply this process, we're always going to flip the parity of L. So if L is odd, then we're going to get L even, and then if L is even, then L is odd. So that essentially shows that the number of L colourings when L is even is the same as the number of L colourings when L is odd, because there's a sort of one-to-one correspondence, as you can see from applying this process. However, as I said, there's one case where this process doesn't work, i.e. we start with a valid solution, apply this process, but we don't get a valid solution. And that's in the particular case where L is 0, and our colouring is this thing here. So we have our chessboard, and our first n squares are red, and of course there's L is 0, so there are 0 green squares. So we've got something that looks like this. So let's look at the case n equals 4, say. And then all the other squares are blank. Then if I apply this process, well, I'm going to go to the rightmost coloured square, which in this case is this nth red square. Rub it out, and then put a green there. But notice that this thing here is not a valid solution, because it contradicts this final property. There is not a blank square left of the leftmost green square, because obviously all those squares there are occupied with reds. Okay, so this thing doesn't work. I have the valid solution where the first n are reds, but then if I try and apply this process, I don't get a corresponding valid odd solution. Okay, in particular, that means that there's one more L colouring when the case L is even than there is in the case where L is odd. So then we can conclude the equality, this thing here, let me get rid of this, that the sum from L equals 0 to n, where L is even, of the number of L colourings, that's equal to 1 plus the sum from L equals 0 to n, L odd, of L colourings. Number of L colourings. Okay, and that is just by the property I just said, that the fact that there is one more L, or when the case where L equals 0, which is obviously even, we have a valid solution, but then there's no corresponding one, because in the case where the first n squares are red. Okay, and that proves this equality, and by the fact, the thing that we just did, the number of L colorings is this thing here. We just plug that in and we get the desired equality, and that is the problem solved. I think it was quite a nice solution using combinatorics and sort of this fictitious setup of a chessboard. But yeah, it was quite nice. I hope you enjoyed the solution. As I said, there are a few different ways you can solve this problem. Do it a bit more algebraically, and if you want to look into it a bit more, I recommend you look up the Chu-Vandermonde property. I'm not sure if I pronounced that correctly. I'll leave a link to perhaps a Wikipedia page or something in the description below. Apologies for the darkness. I did try and film this with the windows open, but there was too much reflection against the whiteboard. So this was the best sort of visual quality I could get, but it came at the sacrifice of a bit of light. Anyway, I hope you have enjoyed this video. I went on a little bit at the end for no reason. I hope you have enjoyed this video. If you are new here, please do consider checking out some of my other videos and subscribing too if you haven't already. I make lots of fun maths videos, not just these solution ones. But yeah, I will catch you in the next one. Have a really great day.